Hey guys, this is Academic Chemistry, Chapter 5, Section 2, Arrangement in Atoms, and this is Part 3. So you've already gone over two ways to do electron configurations. The first is using that diagram, you drew diagonal arrows, and then the second time was figuring out how to use it on the periodic table. So today isn't really going to be a way to figure out electron configuration, more just understand better why we know how this happens and what happens. So there's three main rules for electron configuration. The first is Aufbau's principle. And what this says is all electrons occupy the lowest orbital that it can be received in, or basically that it can fill. So if you remember when we did the electron dorm activity, you always gave students the cheapest room. So this is the cheapest energy. So basically, what's the closest to the nucleus and the easiest path? So it's not always just the closest to the nucleus, but it's whatever has close to the nucleus, and it's a simple configuration, a simple orbital shape. The next one is Pauli's exclusion principle. What Pauli's exclusion principle says is if two electrons are in the same orbital, they must have opposite spins, so that way they occupy different areas within the orbital. So I think of that as an analogy would be if you're going on a highway, right? You can either be going north or south. Now let's forget about east-west, so that makes it more confusing. If you're driving north and someone else is driving south, if you stay in your lanes, you'll never hit each other, right? So think of that as when your electrons are going around, think of each orbital as having two lanes, right? A north lane and a south lane. So that way those electrons don't bump into each other. You can't have like charges hit each other, they're repelled. So they have different spins, so they're actually occupying different space within each subshell or each orbital. Then there's Hunds rule. Hunds rule is orbitals of equal energies are each occupied by one electron before any orbital is occupied by a second. So this is back when we did the electron dorm, how you had to fill up each spot in a subshell or SPD before you went back and paired people up in the rooms. So some people call this like the empty bus seat rule. If you ever ride a public bus and you look around when you get in, if there's an empty bus seat, you're going to sit there before you sit with someone else, right? So this is just whatever, when electrons can have an orbital to themselves, they will. They won't pair up in the same orbital unless that's the only option they have. Also, remember that all electrons in a singly occupied orbitals, so this doesn't have to deal with S because S only has one spherical orbital in a shell. But if there are multiple orbitals, like P has 3 different orbitals, or D has 5 different orbitals, F has 7 different orbitals. So the other part of Hund's rule says that all electrons that are singly occupied must have the same spin. So you always have a positive spin in each one, and then you go back and fill it with your negative spins. So an up spin, up, 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 then you go back and fill down spin. So we have these things called electron configuration maps. So that's what you're seeing on the screen here. And you notice that there are some dashes and some numbers. Let's go over what they are. So each of these lines, these dashes here, they all represent an orbital. So if you notice 1s, S only has one orbital, so that's why there's only one dash, versus 2p, there are 3 of them because there are 3 different orientation of p's and every energy level, which brings you back to lines are labeled with the energy level, N, and the orbital shape, so S, P, D, or F. Notice in your first energy level, you just have S. In your second, you have S, and you have 3 P's. In your third energy level, you have S, P, and then you have those 5 Ds. In the fourth and on, you would have S, P, D, and the 7 Fs. So when you fill this map, the arrows are going to be used to represent electrons. So the direction of arrows indicates the spin. So a positive spin has an up arrow, a negative spin has a down arrow. Let's do our first element and chart out its electrons. So hydrogen. How many electrons does hydrogen have? Well, you look under the periodic table and right here is a 1, so it has 1 electron. The first thing to ever spin is always ever fill is 1s. So there's your electron. Notice it has an up spin. So in hydrogen, you just have 1 electron in the first energy level in an s orbital, meaning a circular shape, and it is spinning in one direction. So the electron configuration notation would be 1s1, because that's all you see in 1s. You've got 1 arrow or 1 electron, so 1s1. All right, helium. Helium has 2 electrons. The first one always goes in 1s, and it's always an up spin. The second electron has to fill this subshell before you can move on. So 1s with a down spin. So you have 2 electrons in your 1s, so the electron configuration is 1s2. All right, beryllium, 4 electrons. Here we go. The first 2 always go in 1s, and then you come down to 2s, fill with a positive spin first, and then your down spin second. So 1s2, 2s2. The next one we're going to do is nitrogen. So nitrogen has 7 electrons, which means it has those 4 electrons we've already charted out. Those are always going to fill in this pattern. And then you have 3 more to go. So the next thing to do is 2p. Now this is my 5th electron. I have 2 options to put my next electron. I can either put it here in the same orbital as 2p or give it its own area in its own 2p. And according to Hunds' rule, I have to put electrons in each orbital by themselves before they fill up. Think about electrons as being kind of jerks. They don't like to share their space unless they have to. So this electron, the 6th electron, goes right here in 2p in its own orbital. And so does the 7th electron right here in 2p in its own orbital. So notice in nitrogen, in an atom of nitrogen, you have 3 electrons occupying their own orbital. So all electrons in the 2p subshell are in their own orbitals. They're all positive spins. No electrons are paired up in 2p. All right, if you count this up, 1s, 1s2, 2s2, 2p, and you count all of them in 2p, and you have 3. So 2p3. Let's do a harder one. Titanium. So titanium has 22 electrons. All right, I want you to watch carefully as you fill all 22 electrons, because this is the basic pattern for filling electrons. So we've already done the first 7. So notice we have empty spots in 2p, so those have to fill up before you can move on to 3s. This takes up our first 10 electrons. So the 11th one goes down to 3s, the 12th one, and then the 13th, 14th, 15th. Notice again, we had to fill all positive in all of our 3p's before going back. So now we go back. Then you go to 4s and you're like, whoa, what just happened? Okay, so this is saying that you have to fill the lowest energy levels first, or whatever takes the less energy. So even though this is in a higher energy level, it takes less energy. If you remember back to the electron dorms, you filled a 4th floor studio before a 3rd floor den, and that's because the 3rd floor dens cost more. Well, same thing here. It's less energy to do a 4s than a 3d. The D-shaped orbital is really complicated, so it takes a lot of energy for an electron to go back and forth like that, versus a 4s is just in this spherical pattern. So even though it's spread out more, meaning it's reached a higher energy level, which is further from the nucleus, it takes less energy to do it because it's less complicated of a shape. So you fill 4s before going back and filling 3d. So that's the electron configuration for titanium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. Let's look at another map to figure out why that is. So this electron configuration map looks really similar, but this one is actually done by increasing energy, not just energy levels. So let's zoom in really quick. And if you notice here, 3d requires more energy than 4s. So as you go up, you're going to fill in the order of what you hit things, so you're filling with the least energy level or the least energy required orbitals rather than just by energy level. So let's go over titanium. Titanium has those 22 electrons, and we've already filled them, so I'm going to go kind of quickly for the beginning. And notice 4s right here fills before 3d because it's lower. This takes less energy, and then you fill 3d. So that's by energy, so you can kind of see where that came from. All right, for the last element, yttrium, I want you to figure out where you think those 39 electrons go. Freeze your computer, and when you come back, we'll go over it. All right, so we've got 39 electrons to give out. For the 39 electrons, the first, second, third, fourth, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th, 13, 14, 15, 16, 17, 18, 19, 20. Did you get that? 21, 22, 23, 24, 25. Then go back 26, 27, 28, 29, 30. 31, 32, 33, 34, 35, 36, 37, 38, and 39. So here is your electron configuration. Hopefully you got that, and make sure you talk to a teacher if you have any questions. Good luck with electron configuration.